Stop everything that you're doing and train your own reasoning model. That too for free on a Google Colab notebook if you can wait for 1 or 2 hours. Or if you can spare like $3 to $5, then you can get it done even within like 15 to 20 minutes. We're going to see how you can take an existing model, a 3 billion parameter model. In this case, I'm going to use a Qwen model, and then train that into a reasoning model in the style of DeepSeek R1. So the reasoning model will have reasoning tags where if you ask a question, it will understand, contemplate, and then finally give you an answer back. This is something that has been possible because of a lot of researchers, and finally Unsloth has put together everything with memory efficient tutorial, and we are going to follow that particular tutorial. I'm going to share the Google Colab notebook with you that you can just click from the YouTube description, straight away start running it. You don't have to make any changes, but along the way I will also explain what kind of changes you can make if you want to customize it, and also what kind of failures that I got while going through this exercise. I spent like a lot of time, lot of credits, GPU credits on this. So there is going to be a lot of information nuances as part of this tutorial. First of all, this is the Google Colab notebook. This Google Colab notebook exactly runs on T4 machine, but if you have got Google Colab Pro, then you can go to a higher tier. Now the very first thing that you need to do is you need to install Unsloth and VLLM, and everything else is going to help you to run this based on the compute that you have got. So diffusers is required for you to install if you're running this on a 4090 or any other local machine, like maybe you want to run it on Model Labs or Unpod, then in that case you have to install diffusers as well. But if you're running this on Google Colab, you don't have to install diffusers. And TRL is primarily for the GRPO algorithm, which is the group relative policy optimization, which is the reinforcement learning algorithm that we are going to use to train the Qwen model in this particular case. And there is a patch that is required for the Unsloth models. So from Unsloth, import fast language model, which is to load the model, and patch fast RL, and we are going to just patch the GRPO algorithms. And the next step is for us to load the Qwen 2.53 billion parameter model. And this is, in this case, we are going to load an instruct model, but I would strongly encourage you to try the same thing with base model as well. So you can experiment, see different things, how it works, and what kind of things give you an improvement over the base model. Another important thing that you have to notice is this is right now on Google Colab. So that is exactly why I've used a 3 billion parameter model as a default model in this case. But if you have got a longer compute or a bigger compute, more compute, it's better if you use like an 8 billion parameter model or a 7 billion parameter model. So you can go ahead with the Llama 7 billion parameter model. So the way we can do this better is to have a larger model and also have a lot of parameters getting trained. What does it mean? It means there are two things that you can actually do to improve the model, but that would also require a lot of compute. So one is you can increase the sequence length. So people have realized that as you increase the maximum sequence length, the reasoning traces can become better. So if you want like longer reasoning and you want the reasoning to be better, then you can have a maximum sequence length to be 1024 or something bigger than this. But let us say you don't have a lot of compute, you don't want to wait for a lot of time. I would say you can start even with like something like 512 or 256 and then see how it goes. The same thing goes for LoRa rank. So the larger you go, better it is, but it is going to be slower. So it's just a trade-off that you want to do. You have to change it in the multiples of 2. So in this case, we have gone ahead with 64. I ran this on H100. This entire notebook was created on H100 and it took about like 20 minutes on H100. I think 1 hour H100 charges are like $3, including storage like $3.5. So basically this is like a less than $2 work, and then you can store LoRa also, which I'll show it in the video. So you can use it every time on a Google Colab notebook as well. At this point, we have imported everything is ready. We're going to load the model. So one important thing here is you have to enable VLLM for fast inference. If your compute, whatever machine that you're using, supports VLLM. If it doesn't support VLLM, make this false. You could come across different kind of bugs saying that LLM shouldn't be pickled, LLM engine shouldn't be pickled. So these kind of errors are primarily from VLLM. So depending upon what kind of error you face, you either disable or enable VLLM here. So if you do not have VLLM, make this false. if you have VLLM, just let it run and then see how it goes. The second thing is we are trying to load the quantized model. So this is like a Q-LoRa fine-tuning kind of a concept. So for you to load the model as a quantized model in itself, we have to say load in 4-bit as true. If you do not give this, if this is false, the model will be loaded in 16-bit instead of a 4-bit. So that is one thing here. And finally, if you are hitting CUDA out of memory, or if you are hitting LLM engine should not be pickled, or LLM engine can't be pickled, something like that, then I would strongly encourage you to reduce this number. So the larger this number is, more GPU compute is required, then the chances of you hitting CUDA out of memory is higher. So if you hit CUDA out of memory, reduce this number. If you do not hit CUDA out of memory, increase this number. And also another thing with Google Colab is every time you want to rerun this, for the first time you have to install all the packages, but after that every time you want to rerun this, if you hit CUDA out of memory, CUDA OOM, then you can just go to runtime and then restart your session. That will basically clear your current memory, and then you can run everything from top to bottom with different parameters. So that will kind of help you understand how, what is the right set of parameters that you want to go ahead with. So this is basically, we have loaded the base model. In this case, I'm using the Qwen 2.53 billion parameter instruct model, not even a math model, the general model, but you can select any different model and then do the same exercise. The only thing that you have to keep in mind is you have to see what kind of target modules match with that particular model, the LoRa target modules, and you can find this easily on internet. Like if you search, you will see for that particular model or local llama, you can see in this particular case, we are going ahead with all these target modules to have a maximum impact. And if you feel that there is any error, then you can reduce couple of LoRa, the target modules, and then you can train the LoRa and then see if it actually works, the reasoning actually works even with the lesser fine tuning and training. So that is basically the model one. And once you have all these things ready, you basically have now a model that is Qwen 2.53 billion instruct model loaded with 4-bit quantization. So that is available. You have defined how the LoRa training should happen. So all the target modules for the LoRa training, everything is done. Now we are getting into the data preparation, which is very, very, very important. The first person who put together this is Will CCB. There is a full name, I'm not sure about it. So what you can do is you can load the data set from Hugging Face's data sets. Here in this particular case, they are going ahead with the GSM 8K data set, which is open sourced by OpenAI, and that is a data set that can improve the math reasoning of the model. But one thing that I'm also trying to do is extrapolate or change this code in such a way that it can help other fine-tuning process. Like for example, can we use it for instruction fine-tuning? I'm still currently in that process, but for now this will work excellently with math related dataset. So you need a system prompt. The system prompt basically says how the entire template should look like. You've got the respondent following format, there is the reasoning, and then there is an answer. You've got the 3 dots here, the ellipses here, and then there is an XML COT format. So reasoning and reasoning, this is like the F string, the reasoning, answer, and reasoning. Answer. So you basically want, like for the perfect reasoning, you need like an open and close tag of reasoning, and then open and close tag of answer, and within open and close tag of reasoning, which is where it contemplates, it does all these things. Now you have some helper function basically to extract everything, and this is exactly where you read the GSM 8K and then finally create the dataset in such a format that it is in the conversational template that can be used for fine tuning. So for you to do regular fine tuning, you usually have a format, and what we are doing is we are taking GSM 8K data and then putting it in the format in such a way that it has this kind of thing and then it can understand. So that is what we are kind of doing here in this particular place. And then the most important section for any reinforcement learning algorithm, one of the most important is to have right set of reward functions. We have 6 reward functions here: the correctness reward function, int reward function, strict format reward function, soft format reward function, count of XML tag, XML count reward function. So in my training process, I used all these 6 reward functions, but I would say that maybe it's a good idea to try with 2 and then see what happens. So you can see in my case, I did this twice. So that's why you see 500 steps. I did one time 250 step and another time 250 step. And then you can see the kind of metrics that got moved. The count reward, XML count reward function moved. The correctness reward function is one thing that I would say that you should focus on. If you see a spike in this and you don't see any spike in this at all, that means probably your model is trying to learn the format, not necessarily reason or not necessarily generalize into reasoning. So even if you see spike in this case, like for example, previously I tried it with a smaller model, a 0.5 billion parameter model. I got training, during the time of training, I got like correctness reward function, like the value of that going up. But still, after training the model, when I prompted the model, when I used the model for inference with the LoRa, it did not have any reasoning at all. So that is how I ended up with a 3 billion parameter model. So a very important metric for you to look this reward function model, and also just to like even to know that something is working, I would say first pay attention to that reward. And also something you can look into is the KL divergence. It's basically like how much your distribution is different from the core distribution, like the previous model distribution. If it is too far, it is not very good, but it also tells you that something is working, like the reinforcement learning is doing something. So these are certain things that you should look into it. But I would say, like, okay, you train a model, but you can try with like 2 reward function as well. Like one is this, the second one is the format, and then see how it goes. Basically, all these reward functions are designed in such a way that, okay, incentivize the model for what it does correctly and penalize the model. In this case, we're not doing a lot of penalization, but penalize the model if it makes a mistake. So if there is a correct XML reasoning tag, then the model gets like this particular reward function gets a score. If there is the only right answer, the answer itself is right, not about just the format, answer itself is right, then the correctness reward function gets an answer. So you kind of balance between the accuracy and also format, which is exactly what DeepSeek R1 did if you check the paper. Once this is all done, and again, like you don't have to write any of these things. I'm explaining it to you in such a way so that if you were to do this for a different problem, different data set, you can easily do it. In fact, if you see here, here it is a helper function that basically downloads from here. So you can see there is a load data set. This is exactly from where, from Hugging Face's dataset, the dataset is loaded. So one of the easiest experiments that you can do is, instead of using GSM 8K, you can try something like ultra chat, ultra feedback, different kind of dataset, and then see how it goes. Now this is done. Now as a part where we are going to define the training parameters, this is very similar like what we do with typical fine tuning. Again, if you were to use VLLM, make it available here. If you don't want VLLM, just make it false. These things you can directly go ahead with all these steps. If you have bfloat 16 supported, go ahead with bfloat 16. I don't think Collab supports bfloat 16, so in this case it will automatically default into FP16, and I think bfloat 16 gives you a slight advantage in terms of compute size. Another very important metric that you can play with if you hit any out of memory error is this one. So this is the number of the batch size that it is using to train. One important thing is the batch size. This one multiplied by this one should be of the multiples of this. Okay, 4 into 1 should be divided by 4 here, number of generations. I mean, at least that's what the error I was getting continuously. So batch size can be like 4, 2, 1, 2, 4, 8, 16, 32, 64. I did this on an 8 GB VRAM and even on 80 GB VRAM H100, and even on 80 GB I couldn't run this with 32. I couldn't run this with 16. I couldn't run this with 8. I should have ideally been able to run with 8. I don't know what was happening. So play with this training batch size. That will help you do the training process much faster. So if you get a bigger machine, don't go ahead with the same size. Go with a bigger one. If you do this thing on Google Colab, if you are getting an error, so I would just immediately make it 1 and then run the same thing. And the next thing is the number of generations. This is also something that will increase the memory consumption. So if the number is giving you out of memory, reduce the number. So that's another thing that you can do. I think rest of the things that you can keep it as it is now, but if you have a long context model, then you can try and then do a different thing. Another important thing is, if you want the full training to happen, then keep the number of training epochs to 1. But if you want like the partial training to happen, then you don't have to specify number of epochs. What we are doing here is we are going to train this model for 250 steps for a 3 billion parameter model, or even like a slightly bigger model for at least like 150 steps. The training process is going to be quite unstable. You may not even see any kind of a spike. So for example, if you see in my case, when I was training the 0.5 billion parameter model, at least until like 100, I didn't like see a lot of traction here. So everything started after 100, and the same thing here. You can see the count increasing like quite spiky only after 150 steps. So I would say better to go with 250. But if you have a larger model like 8 billion parameter model, I wouldn't hesitate experimenting with 150 steps as well. Then save the number of steps at what point you want to save it. Go with the same maximum grad norm. And if you want to use weights and biases, in this case I used weights and biases for model monitoring and reporting, which is quite easy to manage. You can go with that. Otherwise you can just say none. If you do weights and biases, then you have to also pip install weights and biases before, which I don't think it's there in this notebook. If I remember correctly, yeah, it's not there. So if you want to use that, you have to have that. Otherwise, just go ahead with none. Unsloth itself gives you some reward functions available, so you can just check it out. And you can have a run name. So the run name is going to just help you with, if you are on weights and biases, you can see the run name. I've just called it Quen Baby. For some random reason, I was very sleepy. So if you are doing it with Unsloth, this is how you would see. You would see the training loss. You would see reward should ideally go up, and then you can see KL divergence changing, and then completion length kind of like fluctuating. Once everything is done, our training argument is fixed. Now we have the GRPO trainer. This is where you specify what is the model you're going to fine tune, what is the model you are going to use for tokenizer, basically the tokenizer. Then what are the reward functions that you want to use this model to drive into that particular direction, what are the training arguments which we just defined above, and what is the training dataset which we just created above. So you can see we created the training dataset there, and once we have that, the model training process is going to do. Unsloth is pretty fast, to be honest. Like one of the easiest ways for you to do this thing is Unsloth. I did the same thing like 3-4 days back. I struggled a lot to do. Unsloth has made it really easy. So as you can see here, it's starting with the training process. And you can see in my case, I did a 250 250 steps, and this is 21 minutes 43 seconds on H100, the machine that costs about $3 per hour. And you can see the reward starting to go up, and it kind of stabilizes after a point. And after 250 steps, then you can see for every other question, you will see reasoning tags coming and going. So reasoning tag is there, and a reasoning tag is there. So you can see there is a question is there, then there is a reasoning tag is there, reasoning close is there, answer tag is there, answer close is there. So you can see the model trying to do better, and you can also see the same thing here. But even for a model of this size, you can see the strict format did not occur at all. So that aha moment that we talk about in DeepSeek, for this particular reward function, it did not happen at all. So it's not like the first run you will get everything correctly. So it's a lot of trial and error as well. So I would say experiment with it. That is one of the reasons you can start with Google Colab Notebook, and then maybe go to like a bigger compute machine. Now once everything is done, what we do as part of the process is we would have saved a checkpoint at 250 steps. Now what we did here is we tried to ask a question to the same model, the Quen 2.5 3 billion parameter 4-bit quantized model, and see how the model responds. So in this case, I just asked how many R's are in a strawberry, and then it said answer to the question is how many R's in a strawberry is 2. Just like a random question to understand how good the model is. But this is without what we trained now. Now what we are going to do is we are going to save the LoRa of what we trained. So what we have done is QLoRa, a quantized LoRa, where we have the LoRa adapter separately. And this is exactly what you can download in your local computer and keep it. So there will be like 2 files. You can download them and keep it. I can probably show you those files. So if you see here, I've got these 2 files. So the adapter model and adapter config. So these are 2 files that you can basically download after you train this model. So that is what the save LoRa is. Once you do save LoRa, there will be a folder in your computer that says GRPO saved LoRa, and those 2 files will be there. And you can always use that file with one of these, like the Quen model in this particular case. If you have a Quen model in your local computer, you can apply this on top of that and then run it, or even on Google Colab you can run it. So always save the LoRa. Even if you did not get like a great performance, I would say save it. Otherwise you don't have to like go through the same training process again and again. Now when we apply that LoRa, so you can see here, I've applied that LoRa, almost like similar setting, but applied that LoRa and asked the question, which one is bigger, an airplane with 10 kgs or two travel bags of 5 kgs? And when we do the same thing, you can see here, when we do the same thing here, you can see the reasoning tags come into picture, and it starts doesn't reason like in a higher level like DeepSeek R1. I mean, we can't compare like a 670 billion parameter mixture of experts model with the 3 billion parameter model. I mean, that would be ridiculous if that happens. Maybe in the future, but not today. But you can see the reasoning aspect comes into picture. So there is an open tag, there is a closed tag. Still, there is not a closed tag for answer, but still it just kind of goes into that direction. Okay, to determine which is bigger, an airplane with 10 kilos or two travel bags of 5 kgs each, we need to compare their weights. And next line. The weight of an airplane is 10. The total weight of two travel bag, each 5 kg, is calculated as follows. 5 plus 5 is equal to 10. Both airplane and the two travel bags have the same weight of 10 kgs. Now, reasoning is finished. At this point, it has an answer. Answer starts. The airplane and the two travel bags have the same weight, 10 kgs each. Neither is bigger than the other in terms of weight. It's kind of a trick question, but it gave me right answer. See, mind you that this is not a Quen math model. It's not like a programming model. This is just a normal Quen model. We have trained it with math dataset, and it seems to be working. And this is basically the aha moment or whatever that they've been discussing about DeepSeek. So this is one of the easiest ways you can train your own reasoning model, or a model that you can train to reason. Any LLM, you can pick any LLM like Mistral, you can pick Quen, you can pick Llama, 5.4. I want to do the same experiment with 5.4, which is a 14 billion parameter model, and then do this. At this point, you can go ahead and then save the model. You have to get the Hugging Face token here. So after you get the Hugging Face token, you can go save the model in Hugging Face as well. If you want to convert into GGUF or Llama CPP, you can convert and keep it. That means you can use that as part of your, let's say, Llama or LM Studio or any Jan or any other thing. Overall, I'm not sure how much time I took, but overall, this is an excellent, fun project. If you want to spend 2 to 3 hours in the weekend, and again, you don't have to you don't have to literally, I mean, it's fun to see these graphs going up and down, but you don't have to do that. You can run this and then just, watch a movie or a series or whatever that you want to do. But it's quite fun. It's very interesting to see what kind of things that you do. Every other day there is a new research coming. Like, some people have figured out there is another way. Just with prompting, we can kind of elicit a reasoning kind of a response. I'm looking into it, but for now, if you want to use a free resource and train your own reasoning model, this is one of the best, easiest, cheapest way. And if you can spend $3, this entire thing is going to take 20 minutes for you to do it, and then you can enjoy the model and then see how the model is going to perform. I hope this was helpful to you. I'll link the Google Colab, the Google Colab notebook, the Unsloth blog post, and also my weights and biases in case if anybody is interested. But otherwise, see you in another video. Happy prompting.